we are going to cross a river. So, and the velocity of the river with respect to the Earth is going to be 5.0 meters per second east. So the river is going to be going this direction at 5 meters per second. That's the velocity of the river with respect to the Earth. Now, the next question is one that sometimes people struggle with, so I'm going to make sure we understand. Remember, the river is flowing eastward. All the water is flowing that way, eastward. We're now going to draw the shore of the river. And the question is, do I draw the shore of the river like this? Or do I draw the shore of the river like this? Think about it to yourself here for a second. If the river is flowing eastward, am I going to draw the river shore this way? Or am I going to draw the shore this way? Please illustrate with your hands. Right? It's a basic thing, but the water flows parallel to the shore of the river. So I'm going to draw the shore of the river like this. We are going to navigate a boat. The velocity of the boat with respect to the river is going to be 7.0 meters per second north. So I'm going to take and draw the velocity of the boat with respect to the river like that. In other words, the river is flowing to your right or eastward at 5 meters per second. I'm going to take and navigate a boat directly north at 7 meters per second. So please point in the direction that the boat is actually going to travel. Does this feel familiar? Yes. It should. This is just like the advanced airborne example we did when I first introduced vector addition. And there's a reason for that. I do this because you should understand that what we're doing today is still vector addition. It's almost the same stuff, we're just calling it something slightly different. It's relative motion. So we are figuring out the velocity of the boat with respect to the Earth. And the velocity of the boat with respect to the Earth is a vector, and it's equal to the velocity of the boat with respect to the river, plus the velocity of the river with respect to the Earth. Where, bless you, the velocity of the boat with respect to the Earth is the resultant vector, and the components of that resultant vector are the velocity of the boat with respect to the river and the velocity of the river with respect to the Earth. Andrew, help me figure out the velocity of the boat with respect to the Earth.
We use the Pythagorean theorem.
Which is?
A squared plus b squared equals c squared.
And what are A, B, and C?
A is velocity of the boat with respect to the river.
Squared plus?
Yep. Plus the velocity of the river with respect to the Earth.
Squared, which is equal to?
The velocity of the boat with respect to the Earth.
Great. So the velocity of the boat with respect to the Earth then is equal to the square root of the velocity of the boat with respect to the river squared plus the velocity of the river with respect to the Earth squared. Velocity of the boat with respect to the Earth equals the velocity of the boat with respect to the river is 7 squared. Velocity of the river with respect to the Earth is 5. If you're going to square the square root of, we get the velocity of the boat with respect to the Earth.
9.1651.
I'm sorry, I missed the beginning.
9.165 Joule.
So the velocity of the boat with respect to the Earth is approximately equal to 9.2 meters per second. Nate?
You're going to want to find the angle of that.
I agree with that. Why are we going to want to find the angle? What is it about the velocity of the boat with respect to the Earth that says we need an angle on that? Victoria?
We need a direction.
Yes, but why? I agree with that, but what is it about the fact that we're solving for the velocity of the boat with respect to the Earth that means we need a direction? That's okay. Nate?
It's a vector, so it has that magnitude and direction.
Velocity is a vector, so we need magnitude and direction. George?
I get something different.
Right. So you should be all doing your calculator calisthenics and checking to make sure that we're doing the right math on the board. This is not the right answer. That's why I count on the some 30 odd of you to be doing this so that we can make sure we have the right stuff on the board. What'd you get, Victoria?
8.602325.
60325
267.
267?
Yeah.
All right, I'll put 27. And then with sig figs, we get 8.6 meters per second. Is that correct? George, is that what you got? Great. Okay, so now we need the angle. We're going to figure out that theta that is right here. Please help me figure out the theta, Aaron.
Well, you could use.
I'm sorry, I said Aaron.
Oh, Aaron.
Aaron,
Okay.
yes. Ms. Warwood.
Okay, you could use cosine of theta equals adjacent over hypotenuse.
What is it, adjacent are theta?
Velocity of the boat with respect to the river.
Divided by the hypotenuse, which is?
Velocity of the boat, Earth, with respect to the Earth.
With respect to the Earth. Therefore, theta is equal to the inverse cosine of the velocity of the boat with respect to the river divided by the velocity of the boat with respect to the Earth. Theta is equal to the inverse cosine of the velocity of the boat with respect to the river, which was 7 divided by the velocity of the boat with respect to the Earth, which we got to be 8.603257.
$35.5462 degrees.
That's plenty. So with sig figs, 36 degrees. 36 degrees what, Julia? What's the direction on that?
East of south.
East of south. Let's see if I agree with that. If we draw our compass rose here, this is north, south, east, and west.
East of north.
East of north, right? Because this is east from north. Great. So it's east of north. That is the velocity of the boat with respect to the Earth. Part B. If the river is 250 meters wide, which would be the displacement in the y direction, and remember we're crossing the whole river, going all the way across, the question is, how far did we travel? How far did we travel? If we're going all the way across the river and the river is 250 meters wide. Who's got an approach for me? How to solve this? Sam.
I would find the time it takes to travel straight across.
We could. We're actually going to do that second. We don't have to find the time. We could do it that way. We'd be doing 2 steps. We're going to figure out the time second here. Stuart.
You do a vector triangle with, the angle is 36 degrees. And the left side of the triangle, like across the river, is 250 meters.
Cool. Hold on. So we're drawing a new triangle?
You could use the same one, just with different numbers, but...
I wouldn't suggest that. That's going to confuse people in the long run. Because you should have a triangle that is, for example, all velocity, because all velocity, and then a triangle that is all, that's all
meters.
displacements, right? Okay. So let's redraw this. We've got a triangle that is the displacement in the y direction. This is going to be a similar triangle. And we have the displacement along the hypotenuse, and we have the displacement in the x direction. This would be how far downriver we're swept, which is not something I asked for, but you can see it's there. And this is a similar triangle, and the hypotenuse, I'm just going to call delta d for the displacement along the hypotenuse. Now, considering the fact that we have a similar triangle, Tristan, how are we going to solve for delta d, or how far we've actually traveled?
With sine. So sine of theta is, cosine. Cosine theta is adjacent over hypotenuse.
What is it? Adjacent r theta?
Theta is...
Adjacent r theta, we're going to fill in here.
Change in y.
The displacement in the y direction divided by?
Total displacement.
The displacement along the hypotenuse, which I've called delta d. So we could solve for, we're looking for delta d here. Let's solve for this. Cosine theta equals the displacement in the y direction divided by the displacement delta d along the hypotenuse. We can multiply both sides by delta d. That cancels out on the right-hand side. We get the displacement along the hypotenuse times the cosine of theta equals change in y. Divide both sides by the cosine of theta. And we will solve for the displacement along the hypotenuse, change in y over the cosine of theta. Change in y is 250. Cosine of our angle, which was the 35.54632. The displacement along the hypotenuse, please.
I got 7.03, which is wrong because I did cosine. Never mind.
You've got, yeah, that would do it. Jordy?
307.2590090.
Independent confirmation?
Yeah.
Great. Okay, so 310 meters. Now, that is the answer to how far did we travel. We do not need a direction on that. Why not? Sam?
It's a scalar.
What's the it? I agree, but what's
distance?
How do we know we're asking for a distance? Because it doesn't say distance.
It says how far.
How far? And remember, far doesn't have any direction on it. It's just a distance. So because I'm asking how far did we travel, it's now not asking for the displacement, but rather just the distance, which is a scalar. Okay, part two, I want to figure out how long did it take. How long did it take to cross the river? Nutrition, how do you want to approach that?
We have the distance and the velocity, so we can find the change in time with those, and that's the velocity equals the displacement over time.
So let's start with the equation velocity equals displacement over time. Now, which velocity are you talking about?
The velocity of the boat in relationship to the Earth.
Okay, the velocity of the boat with respect to the Earth, which is right here, is equal to what displacement? What displacement divided by delta t? So which displacement?
Delta d.
Delta d, the displacement along the hypotenuse. If we're solving for time, we can solve for that. We get delta t is equal to the displacement along the hypotenuse divided by the velocity of the boat with respect to the Earth. So he's taking the velocity of the boat with respect to the Earth and the displacement along the hypotenuse and solving for delta t. That's equal to our 307.25901 divided by the velocity of the boat with respect to the Earth, which was 8.6032527. Please. With sig figs, 36 seconds. Okay, that's one way to solve for it. What is another way? It's very similar, but it's important to understand that there is another way to solve for this time that's not exactly the same as this, but it's close. Same.
Could you have solved for the change in y for time and the change in x time?
Okay, hold on. So we start with velocity equals delta x over delta t. What velocity are you talking about using?
The velocity of the boat with respect to the river
is equal to what displacement?
Delta y.
Over the change in time. So notice, we can use whichever velocity and displacement we want to as long as we're using the same side of the triangle. So this is going to get us delta t is equal to the change in y, the displacement in the y direction divided by the velocity of the boat with respect to the river. So the change in time is equal to 250 divided by 7, which equals
35.7143.
36 seconds, or exactly 35.7143 seconds, exactly what we got before. So notice, as long as you use the same sides of the triangle, it doesn't matter which velocity and displacement you use. We could have even used the velocity of the river with respect to the Earth, except if we didn't know how far downriver we were swept. We could have figured that out. So there are all sorts of different ways to get to the answers in this particular problem. But again, I want to just review that there's really nothing new today. It's just that we're talking about relative motion and using these different subscripts, but it's still just vector addition and constant velocity equations.